Now we're going to look at the graphical side of statistics. So what we do with the data that we got using graphical methods, since we've already done numerical. Here there are two basically types that we're going to be looking at. So firstly, there's univariate, and secondly there's bivariate. So as the name kind of suggests, univariate is when you just have a single piece of data. So if my sample is the heights of people in the class, so heights of people in class, since that's just going to be maybe in centimeters, so whatever, 170, 175, 180, just a list of numbers. Or of course it could be, as we did with the hair color, that's not a number. That's just going to be a list of rough colors. But the main thing is that it's going to be a list of single pieces of information. Bivariate, on the other hand, is when you have two pieces of information. Or a pair, or pairs of. So, for example, I have a data set for the average global temperature, and there that data set is the date and the average temperature. So date and average temperature. Because I want to see how that's changing. If I didn't have the date, if I just had a list of temperatures, what would that mean? By having the pair, I can look to see whether there's any relationship, whether as the date is changing, the temperature is changing. So whether there is global warming happening, and maybe even try and predict what the temperature is going to be in the future. So there are these two, in the same way that we've looked at statistics, we've broken that into graphical and numerical. And when we did numerical, we looking at the central tendency, the mean, median, mode stuff, and also the variance stuff, so the standard deviation range and interquartile range. So here, when we're looking at the graphical, we break it into two subcategories, univariate and bivariate, and then do a quick treatment of each of these. So when we're looking at univariate, we typically would like to plot a frequency diagram. And since heights are normally distributed, we probably end up with something like this. If we had a very large sample, so for just a class, it might look slightly different. So we can either do a histogram and have a collection of bars which should kind of have this shape, or so we'd most likely actually just have a histogram when we plot the data for a class, and so we'd have a collection of bars. So it would be, there'd be many people there in near the middle. There might be two which are like that, but then it would fall off. There'd be less people who'd be smaller, shorter, and less people who would be taller, and then there might be one extreme. So plot a histogram, and that would kind of represent our data when it comes to univariate. When we're commenting on a histogram, one of the parameters, or one of the things we'd look at, is symmetry. So for the heights of people, that is typically a normally distributed thing, and that is symmetric. On the other hand, there are other things which are not symmetric. So there you could have, it begins like a normal, but then it actually continues far further in one direction. I think that that's the case for say wealth distribution, because you'd have the average, but then the tail doesn't stop as quickly on the right hand side as on the left. So I mean, if the average say income is 30 or 40,000 euro, the poorest person, or the most you can go left is say 0. But you can be earning, you have people who make 80,000, who make millions, who make hundreds of millions, even billions. So the right hand side continues a lot further than the left. So when things are not symmetric, we call that skewedness. Otherwise, you can have the case where it's skewed to the left hand side as well. And that's all we do when it comes to plotting univariate. So plot the histogram, or you can plot the data points and just draw a line that way as well. And when we're commenting on it, we note symmetry or skewedness. For bivariate, we use scatter plots. So since we have two numbers in the example I'm going to be looking at, we can plot x against y. So if our two data items are x and y, and then we can look to see whether there's any pattern. So it could be something like this, and there we just say there's no pattern. Or no correlation. So knowing what the value of x is doesn't tell us anything about what the value of y is going to be, or knowing the value of y doesn't tell us anything about x. They seem to be all over the place. If you have the data lining up basically along a straight line, which is increasing, we say that they're perfectly correlated. So perfect correlation, perfect positive. You can also have perfect negative. So there, as x increases, y decreases. And we can also have weak correlation. So we can say weakly positive. Where you'd end up with data which is kind of lined up, but there's noise around the line. So you can imagine drawing a line through that which seems to fit the pattern, but there's not all the dots fall on that line. So that's weakly positive, and you can have weakly negative, where you just have the line going down and the data points noisily gathered or roughly around that line. So that's weakly negative. We say that the correlation ranges from -1 to +1. So a correlation of 1 means it's perfectly correlated, and +1 means it's perfectly positive. -1 means it's perfect negative. So 1 means perfect correlation. Plus is positive. Minus is negative. And that's pretty much all we have to do. So we look at the data. If it's univariate, we want to plot it either using a histogram or just counting, where we just count the frequency or how often the data points occur in certain bands, and then we look at the symmetry and skewedness of the data and comment on that. Well, if it's bivariate, then we use scatter plots. I didn't say this kind of plot is known as a scatter plot. And then we comment on what the correlation is, whether there's no correlation, whether there's a strong or weak correlation, and whether it's positive or negative. The final point is that a correlation doesn't mean things are causal. So correlation does not equal or imply causality. Since what often happens is that there's an underlying thing which variable x and y are correlated to. So as the underlying thing changes, both x and y change. But x doesn't cause y. If you think of inflation, so when there was the boom on, if you plot the price of coffee against the price of sandwiches. Well, suddenly coffee prices shot up since people had more money, and the cost of everything shot up. So if you were a shop owner, you were having to pay far more for rent. So you couldn't keep your shop open if people were paying the same amount for their coffee, because your costs, your rent and your costs for everything, wages and so on, had all increased. So suddenly the price of coffee shot up, but so did the price of sandwiches and actually nearly everything. So if you were to plot the price of coffee, price of sandwiches, the price of pretty much everything, it increased. So you would have a correlation between the price of coffee and the price of sandwiches, but the price of coffee didn't increase, was not the reason that the price of sandwiches went up. So the final thing we have to do to finish up on statistics is the back-to-back stem and leaf plot, which we do next. So stem and leaf plots are a handy way of looking at distributions. So if you have a univariate data set, so it'll be more for univariate, then we can just kind of see what the frequency distribution is. So we're going to look at 3 stem and leaf plots building up to the back-to-back. So the first one, well, we want the data set. So imagine you have a class with 10 people, just because it's easier. It's the same process if you have 25, 30 or whatever, but that's just more hassle and we don't really need it. So say we had marks out of 25, so 5, 11, 14, 18, 20, 15, 8, 17, 11 and 23. So if I had that data, then the stem and leaf plot would be, well, we'd have the stem and the leaf. Let's say the key, so one, the stem, that line 6 means 16 marks. And now we just fill out this table. So the leading figure can be 2, 1 or 0. So if it's a single digit thing, then we put it on this row. If it's anything from 10 to 19, we put it on this row. And if it's anything from 20 to 29, we put it on this. So we just enter these figures into the table. So 5 is going to go here. 11 will be just 1 here. 14 is going to be 4. 18 is going to be 8. And again, we only write 8 instead of 18 because the number of entries we put in is going to be the frequency. So if we'd written 11, 14, 18, then that would be 6 times longer than 5. While there's only 3 numbers put in, so it should only be 3 times longer. So that's why you only put 1 digit. 20 is going to be 0. 15 is going to be 5. 8 is going to be 8. 17 is going to be 7. 11 is going to be 1. 23 is going to be 3. So that is a stem and leaf plot. So I'll put 1. A slight variant of this is the ordered stem and leaf. So this is the ordered stem and leaf plot. It is basically the same. I mean, you go through the same process. So you go stem, leaf. The key is the same. Key. So 1/6 is 16 marks. And the leading digits are going to be the same. So 0, 1 or 2. This is 20 to 29, 10 to 19, 0 to 9. The difference here is going to be that we actually order them, hence ordered stem and leaf. So we'd kind of want to first have done a stem and leaf and then order it. Otherwise it's a bit messy. So we already have the stem and leaf here, so I can just write down the ordered version, reading it off the unordered one. So we have 0 and 3, well, that's ordered. 14, 8, so what I want is 1, 1, 4, 5, 7, 8. There's 1, 2, 3, 4, 5, 6 there. 1, 2, 3, 4, 5, 6. And now they're in order. And this was already in order. So 5 and 8. Now, the reason that you'd want, to order them is because this means you can now read out the median and even, let's say, the range. Because the range is going to be the largest number, so that's 23, and the smallest number, so that's 5. So if it's ordered, the first digit on the bottom is going to be the smallest number, and the last digit on the top is going to be the largest. So it's easy to do the range. If I want to find the median, well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, there are 10 numbers. So then I go, well, it's an even number, so the median's going to be the fifth and the average of the 5th and 6th largest number. Well, this is the smallest, second smallest, third, 4th, 5th. So 14 and 15 are the 2 relevant numbers. So the median is going to be 14 plus 15 over 2. So that's 14.5. And likewise, if I wanted to find out the different quantiles, if I wanted the 4th digit, well, the smallest is 4, 8, 11, 11. So the first quartile is going to be up to the number 11. And then, sorry, it's not the first 4 digits. There's 20, there's 10 numbers. So the first quartile is going to be up to, well, it's going to be between 18 and 11, or between 8 and 11. So then I'd average them. And likewise, I want the 2.5 smallest, or 2.5. I want to move 2.5 numbers from the largest one as well. So it'll be 2 and 3. The third smallest is 18 and the second smallest is 20. So the average is going to be 19. Something along those lines. So that's how we get the ordered stem and leaf. And this is why we'd want it. Since it makes it easier to work out what the median and range and those kind of things are. So then we only have one thing left, and that is the back-to-back. Stem and leaf. So here we need another data set. So we use the back-to-back stem and leaf plot to compare two data sets. So I'll just imagine another class, and the marks there, out of 25 as well. So it's 7, 5, 7, 8, 9, 11. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is my data set B, and I'll call this data set A. And we're using the back-to-back stem and leaf to compare them. So the back-to-back it's basically the same thing. So I do stem, and I have 2, 1, 0. Now I'm not bothering about ordering them, but I could order these as well. So I'll just read this off what I did before. So that's the distribution for the dataset A, and now I add my new data. So here I have 3, 7, 5, 7, 8, 9. Hold a minute. No, that was B. That wasn't a 3. Sorry, it's 7, 5, 7. So I'll just put the 9 there and get rid of that, since how long it is it shows me what the frequency is. And this isn't an ordered thing, so it doesn't matter that I move the digit over there. So then I'm up to 9, and then I do 11, 14, 15, 10, and 12. So the key on this side is key 2, 1 is 12 marks. And the key here is 0, 5 is 5 marks. And I put leaf. So now we have it. That's it. That is a back-to-back stem and leaf plot. Now, what does this show us? Well, on the right hand side, I'd say the distribution is symmetric, and most of it is in the middle. So it's nearly like a normal distribution. While on the left hand side, well, there's nothing, there's nobody got 20 or higher, so the marks are lower. And the same number of people got from 0 to 9 as from 10 to 19. So then we just comment on that, that the distribution B is uniform. So if I was to write it here, B is uniform. Distribution. A is symmetric. peak in center or at center, and I've already said it's symmetric. So that way we can see that they come from a different distribution. I could also add that the range is greater for so here I commented on the middle part, on the distribution, I suppose, but I could also comment on the fact that the distribution A has a bigger variance, that the range, like the biggest and smallest number, is like 23 and 5 for distribution A, while it's more clustered. The largest number is 15 and the smallest is 5. So the range is only 10 on the left. So these distributions are very different. So that's how we construct a stem and leaf plot. And you can do the back-to-back, just the stem and leaf plot, or the ordered. And this is how we use it. And that's the end of our look at statistics.